In this lab, we'll go over the between subjects factorial ANOVA. So recall that this is the design where we have more than one independent variable. In this class, we'll only do the case where we have two independent variables, but you could, in theory, have more than that. And where these variables are fully crossed with each other so that each person is in only one condition. They're in each one level of each condition. I think that becomes easier to understand if you consider a concrete example. So here I have a paper by Orehek et al. Where they were looking at the role of positive affect in the effort that you put towards pursuing a goal. And the background story in this paper is that there's um, different findings regarding positive affect. So being in a good mood with regard to how much effort you put towards a goal. On the one hand, some studies find that positive affect is positively related to effort, such that like where you feel good, this is a good experience, you're going to put in some extra effort. Others find a negative relationship, and those studies argue, well, positive affect signals that things are going well for this goal, so you can put your effort elsewhere. And so what these authors said was, well, the relationship between uh, affect, particularly positive affect, and effort probably depends on whether or not there's another goal. And so they had a two by two design where they manipulated both affect and competing goals. And we can see that in this table here. So affect took on two levels, either neutral or positive, and competing goals took on two levels, either absent or present. So here I have the table of the means, the sample sizes, means, and standard deviations of each of these four cells when you fully cross affect and competing goals, each with two levels, you get four different cells. So we have neutral absent, neutral present, positive absent, positive present. Let's go to Jamovi and look at how to create this table. So I've already had my data set open and I'm looking at my variables here and um, this variable BI is behavioral intention. So that's the motivation. BI, behavioral intention. That's a continuous variable. And that's our dependent variable and it's continuous. And we can see here it's listed as a continuous variable. It's got the ruler next to it. It's continuous. And likewise, affect and competing goals are both nominal variables. And if we click on those, they are both stored correctly as nominal variables. I can see that with these circle symbols. So we're looking good there. We can go ahead and start analyzing our data. If I want to get that means table, I can come up to my analysis tab and go over to exploration and descriptives. I'm getting descriptives on my dependent variable, that's behavioral intention. If I just do that, it'll give me for the overall sample, but that's not really what I want. I want it split by each of these conditions. So if I go ahead and move over affect and competing goals, it splits it by both. And here I have some extra stuff. I don't really want missing or median or min or max. I just want and mean and standard deviation. And that's how I computed that table on the other slide. So then once I have these four means, I can go ahead and plot them, right? I can plot to see what my data look like. When I look at this here and I plot those four means, like this is just the four means from the previous slide, it looks like I have an interaction going on because the lines are clearly not parallel, they're intersecting. But of course, it could be the fact that maybe this graph is zoomed way in and this crossing over effect is actually not as large as it looks. And so really we need a test. We need a statistical significance test to see if this interaction is significant. But just as a glance to get oriented, remember I said the logic of this study was that the relationship between positive affect and motivation. In this case, it's behavioral intention. So that's the behavior, the motivation was the logic, the hypothesis is that that is going to be um, negative when you have competing goals, when you have other stuff to do. So positive affect signals, I'm doing pretty well on this goal. I can reserve my effort here and allocate it elsewhere. So a negative relationship. But they hypothesized a positive relationship when the only goal to complete was the focal goal, when there were no competing goals. It looks like our data fit that pattern at a glance. So what we want to do is go and start probing this and seeing if indeed we have a significant interaction, and if we do, if those simple effects um, support that hypothesis. So the first thing I'll do is I'll run this omnibus test. Now I have the results up here. Let's go over to Jamovi and run it, and then we'll come back here to unpack what they mean. So coming over to Jamovi, I want to, in my analysis tab still, I'm going to come over to ANOVA, and I'm going to do just the ANOVA here. My dependent variable is behavioral intention. I'll move that over. My independent variables, and you can't see, but if I want to select both at the same time, I just hit Control and click on them both, and I can move two over at once. And I get my table here showing that omnibus test. Now, this is the same table that's on the slides on the other slide, so I'm going to go back over there. So we can start to unpack this. I see that I have, my main effective affect. And if I think about that on the plot, that's represented by that red line that's shown there, right? It's the average of affect averaging across goals condition. So if I ignore the goals condition and say, what's the mean in the neutral affect condition? What's the mean in the positive affect condition? And here we can see that that p-value is 0.813. So it's not significant. There is no significant main effect of affect. We do, on the other hand, have a significant main effect of competing goals. That's the average or the middle of that solid line, the competing goals absent, or sorry, present, versus the average or the middle of the dashed line, the competing goals absent. And so that's represented by that vertical red line there. So that effect is significant. So on average, people put forth more effort when they didn't have competing goals versus when they did. And I can say that direction. I can say that because there's only two levels of this variable, right? Because this is just an omnibus test. So it really just tells me that one of these conditions is different from the other. But since I only have two conditions, present versus absent, I can just look at the graph and see, okay, the absent one is clearly higher than the present one. And from this omnibus test main effect, I can see that that is a statistical significant difference. But that main effect, of course, is qualified by the presence of the interaction here. And so what we want to do is dig in and probe that interaction to see what's going on with our simple slopes, simple effects. Here I'm splitting. So I have the effect of affect where competing goals are present. And I have the effect of affect where competing goals are absent. So if I go back a slide or two, where I can see this figure, it's looking at the effect of affect going along the x only within the dashed line and then only within the solid line. So let's go to Jamovi and see how we did this. I want to come and I want to create filters. I want to filter out some of my data. I want to look at only a subset of my data. So I come up to my data tab, there's this filters option. So I want to create a filter that says, I want to create a filter where if I want to look at the effect of affect on behavioral intention, where competing goals equals present, then I want to compute a filter that says comp goals, and you have to say equals twice, equals present. So you can see once I create that filter and I scroll down, it's Xing out all the data where comp goals is absent. So now if I do any analyses, it's only going to do it on these data. So I'm going to turn that off for now. I can turn it on and off just with this little toggle switch. And notice when I turn it on, the results that I computed before, this won't run. This ANOVA won't run because it says, I can't run this because there's no variance in comp goals. Yeah, that makes sense because you're saying throw out all this data where comp goals is absent. So we only have comp goals present. So this old ANOVA that we ran now becomes uh, unrunnable because there's no variance in competing goals. So let's turn that off for a minute. Let's create some more filters. Let's create comp goals equals absent. And then I got to make sure I type this exactly right. Was it ABS? Yes. Okay. So it has to be typed exactly correct. So that's our second filter. And we'll turn it off for now. Now I want to say, well, what if I want to look at the effect of competing goals present versus absent at positive affect? So I need another filter where I say affect equals pos. And I'll create another filter where affect equals neg. So now by turning, oops, see, it's giving me a warning and saying this doesn't work. You have to do two equal signs here. There we go. That fixed it. So now if you look at my data, I have these filters that I can turn on or off to look at only some portions of my data. So going back, if I said, well, I want to know what is the effect of affect where competing goals are present, I'm going to turn on this one. So then when I look at my data, I can see I have only the competing goals present. Affect varies positive to neutral, but all where competing goals is absent gets thrown out. So now if I come back here to my analyses, I can run my ANOVA where I look at BI as my dependent and affect. And then now this is just the effect of affect where competing goals equals present because I've turned on that filter. So I've gone and I've just pasted that here. I can do the same thing, and you see the F was 8.06. I can do the same thing where competing goals equals absent, and I get an F of 4.66. So let's go back here. Let's go back to our data, our filters. Let's turn off the present one and turn on the absent one. So now when I look at my data, I'm only looking at where competing goals equals absent. So when I come back to analyses and run my ANOVA, oops, of affect, I see now I have the effect of affect only where competing goals is absent. And so I've pasted those here. I can do the same thing by looking at the effect of competing goals where affect equals neutral. So I'm looking at the other variable now, the other independent variable, the effect of competing goals absent versus present where affect is neutral. And I can do it where affect equals positive. So I can split my data different ways. But you might be saying, yeah, but I don't look at these mean squared errors. They're all different. I don't want different mean squared errors. Remember, my mean squared error is my estimate of population variance. And my assumption is that it's the same in each one of these cells. And so it shouldn't be bouncing around like this. I should have one estimate of it. And the best estimate is the mean squared error from the omnibus test. And notice that my degrees of freedom now is 76, where before they were only 38. So by using this better estimate of mean squared error, I get more degrees of freedom. So I'm going to go back and I'm going to pop that in to each of them. So now they each have the same mean squared error, and I have 76 degrees of freedom. So then I can just go ahead and compute each f by dividing the mean square by the mean squared error. So in the first one, it's 7.16 divided by 1.03 is 6.96. Moving to the right, 5.45 divided by 1.03 is 5.3. 0.42 divided by 1.03 is 0.41. And 19.04 divided by 1.03 is 18.49. I can then go and say, okay, well, I have an F of 6.96 or 5.3 or 0.41 or 18.49. I have this F statistic with 1 and 76 degrees of freedom. So is that significant? I like to use this graph pad. There's other calculators online. You could look in the back of your book and use the table, but I mean, I think it's easier just to use a calculator and get the precise p-value. So graph pad, if you search graph pad p-value calculator, you come over, we're using an F test here. So you plug in the F, 5.3 with 1 and 76 degrees of freedom, hit compute, and it will give you the exact p-value that you can just pop right in there. So in this case, because there is only 2 levels of each of these, we're done here. We don't have to do any subsequent tests. We can go and compare these results to our plot and say, okay, well, we predicted that the relationship between affect and behavioral intention would be negative when competing goals were present, right? And we can see that that effect is significant right there. Where competing goals are present, the effect of affect on behavioral intentions is significant, 6.96. And I say that it's a negative effect because the line is going down as I go from neutral to positive affect. And I can see that it's reducing. I can just look at that on the plot. I can see that the means are going down. Likewise, I can see here that this effect, this increase from neutral to positive affect in goals, competing goals equals absent, is significant. I can split the data going the other way and say, well, is the effect of competing goals on behavioral intentions significant where people have neutral affect? And we could see, no, that difference there is not significant. There's no difference there. The F is 0.41, and that's not significant. But where affect is positive, there is a significant difference between competing goals present and competing goals absent on behavioral intentions. So I think when you're splitting the data like this, so remember that we're using the computer to split the file to compute the sums of squares, just like we talked about in class. Then we're using the mean squared error from the omnibus test, also computed by the computer, but we're going to substitute that in here. Compute our F's by hand. It's really easy, just dividing. And then using those to interpret the simple slopes. And I think it makes your life a lot easier if you have the plot present to be matching, okay, I'm testing this effect, and I can visualize that on the plot. So that's what I've tried to show you here. Let's do another example. Here we have guinea pigs who received either orange juice or a vitamin C supplement. And they received either a dose of 0.5, 1, or 2. Let's say that is, I don't know, milligrams of either orange juice or vitamin C. And we're going to look at the length of their teeth. How much does these supplements affect how long these guinea pigs' teeth grow? So I have the plot of my means. I have the means in the table to the right there that I got the same way that I just did to explore. Let's open up these data in Jamovi. So I can go ahead and open, let's see, I got to browse, and they are my tooth data set. Looking here at my variables, this could cause you some trouble if you don't pay attention here. So length, that's the length of their teeth in millimeters. It's a continuous variable. It's got the little ruler next to it. It's continuous, looks good. The supplement is either vitamin C or orange juice. It's got the two circles. It's nominal. That looks good. But here's where we have an issue. Dose. Dose is a number, but we're treating it as a category, right? They either got half, 0.5, 1, or 2. But Jamovi just sees a number. So it thinks this is a number and it's going to treat it as a number. But we don't want the software to treat it that way. That will lead us to results that we don't want. So we need to be mindful of that and check when we read this in and say, oh, it's reading it as continuous. I know why it's doing that because it thinks it's a number. I'm going to change it to nominal. Now things will look good. So we could run our exploratory data analysis. We did that before. I'll show you, or I've showed you how to do that already. Let's go to the ANOVA. Remember, I move over the dependent variable. I move over my independent variables, and I get that omnibus table. I've gone ahead and plugged that in here. Again, looking at the plot, I think helps to visualize what's going on in this table. So we have a main effect of supplement. And so what that's saying is that the OJ line, on average, is significantly higher than the vitamin C line. Now, just glancing at this, we can see at dosage equals 2 that that's probably not the case, that they're probably not different at dosage equals 2. But on average, ignoring dosage, the OJ line is higher than the VC line. That's what that main effect is. We also have a main effect of dose. That's represented by the red line that I've superimposed over the plot there, showing that averaging across supplement, so averaging across OJ and vitamin C, there seems to be an effect of dosage on tooth growth, such that the larger dose that these guinea pigs are getting, the longer their teeth are growing. But there is a significant interaction such that the effect of supplement on tooth length depends on dosage. Or another way of saying that the effect of dosage on tooth length depends on the type of supplement. So because we have that significant interaction effect, we can go and start unpacking and probing it. If I split the file and say supplement equals vitamin C, I see I get this significant F test, but again, we're going to be careful there because we don't want to use exactly what's here because I'm only using half the data. And so my degrees of freedom is only 27. So it's telling me about this line that's highlighted in yellow and telling me I have a significant effect here, but we actually want to do this a different way. Before we get there, though, let's go back and revisit how I got these answers. So I just want the one-way ANOVA where supplement equals VC. So I come to Jamovi and I'm going to set up I go to data and I'm going to set up my filters. So I'm going to say, I'm going to create this filter where supplement equals vitamin C. And I'm going to create another one where supplement equals OJ. So now I have supplement equals VC turned on. So if I come over here to my data, I can see the VC data, they're all still active. But if I scroll down, all the orange juice data is all X'd out. So it's like those data don't exist. Jamovi is just ignoring them. So then when I go, okay, let's do an ANOVA, where I want to know the effect of dosage on length, it's only doing that within the vitamin C condition. So it gives me that output. If I want it only within the OJ condition, I simply come back to my filters. I turn off the VC one and I turn on the OJ one. So if I see now all the VC data is blacked out, just the OJ data is active, I can come over to analyses and run the ANOVA where my dependent variable is length, the independent variable is dosage, and it's telling me the effect uh, where the supplement is orange juice, OJ. So that's telling me about the VC line. The OJ one is telling me about the OJ line. But remember, I don't want to just use half my data because I have different mean squared errors. That's my estimation of population variance, but I assume that all these means are drawn from a population with equal variances. And so I want a better estimate of population variance. And what that is my mean squared error from the omnibus test. So I'm going to go ahead and get rid of the sums of squares, the degrees of freedom, the mean squared error, the F and the P, and I'm going to plug in the sums of squares, degrees of freedom, and mean squared error from my omnibus test. And you can see I have now 54 degrees of freedom. So I have more degrees of freedom. And I can go ahead and compute the F, which is just the mean square for dose divided by mean squared error. So 824.7 divided by 13.2 is 62.54. Likewise, 442 divided by 13 is 33. Both of those are significant at p less than 0.001. So I will note nothing actually changed here from when we just split the file manually, but it could have. In different data sets, it will. So we want to do it this way instead of just splitting the file and taking the information straight from the software, because when we do that, we're only working with a subset of the data. We want to estimate our population variance, our mean squared error, right? Our estimate of the population variance based on the entirety of the data. So we see here now that there is an effective dose on tooth length in the OJ condition and also in the VC condition. But in each case, there's 3 levels, 0.5, 1, and 2 of dose. So we can't say that 0.5 is different than 1 or 1 is different than 2, right? We don't know which ones are different. We just know that at least 2 of these are different. So because we have 3 levels of dose now, we need to go another step further. We need to now go do some post hoc tests. Because there's within each condition, there's 3 levels, I would say you could probably just get away with doing Fisher's t-test. So we could go back to our multiple comparisons lecture and say, okay, well, we have this calculator for doing Fisher's t. So in the VC condition, I can go ahead and plug in my means for each group. That was those means I computed on the first page. I have a sample size of 10 in each. My mean squared error and my degrees of freedom come right from the omnibus test. And so I get my Fisher's LSD, and I get specific comparisons for each. So between in the VC condition for I'm comparing where dose is 0.5, the mean is about 8 or so. And when dose is 1, the mean is about 17. And the difference between them is statistically significant. The t is 5.4, where standard error of 1.6, and the p is less than 0.001. Likewise, I can compare the dose of 0.5 to the dose of 2. And that's significant. And I can compare the dose of 1 to the dose of 2, and that's also significant. I can then go and do this again in the OJ condition, comparing, I plug those means in there, 13.23, 22.7, and 26.06, and I can compare those 3 to each other. So when I have three groups as in one of my factors, I have to go through this next step. If it had four or more, we'd probably want to be doing Tukey or Fishers. Or sorry, Tukey or Newman-Cools, excuse me. Because we only had three groups here, we can get away with doing Fishers. But the process would be the same if we were doing Tukey. We would just use the Tukey calculator instead, or the Newman-Cools calculator instead. What if I want to test the difference between OJ and VC at dose equals 2? Like it looks like they're right on top of each other, right? But I haven't tested for that yet. Well, that's just the same thing we went through with the other example. I can go to Jamovi, and now I can create more filters. So if I want to filter for dose, I can say dose equals. Now here we need to be careful because if I say 0.5, I get an error. Argument is length of 0. And I go, yeah, but dose says 0.5. What's the problem? Well, the problem is we've called dose a categorical variable. We've named it a nominal variable. So this needs to be inside quotation marks because it's not 0.5 the number, it's 0.5 the name. Hopefully that makes sense. Then I can create another filter for dose equals 1.0. And I can create another filter for dose equals 2.0. So now, if I want to test, is this difference here, the difference between OJ and vitamin C at dose equals 0.5, I can come to Jamovi, turn on my dose equals 0.5 filter, and I can go and look and see, okay, it's only allowing the data where dose equals 0.5. So here I have where supplement equals VC, and here I have where it equals OJ, but only for 0.5. And so I can come and do my ANOVA, where my dependent variable is length, but now I'm looking at the effect of supplement because I'm holding dose constant, right? So at 0.05, here is that comparison. Now, I probably want to replace this mean squared error because when I do this at 1.0, I'm going to get a different mean squared error. But really, they should all be the same, right? But my point is that once I do that and I replace this with the omnibus test and I recompute the F and I see that it's significant or not, that's it. I'm done because there's only two levels. There's only two levels of supplement. So if it's significant, I can see that the OJ line is higher than the VC line. There's no more follow-up tests to do. So we could do this at 0.05 or 0.5 rather. We can go and change our filters and do it at 1.0. And we can do it at 2.0. And at 2.0, I would expect this P to be non-significant. Even if we haven't changed this yet, even if we haven't done anything, I expect this to be non-significant. Let's see if I'm right. And hopefully it's obvious to you why I think that. And if not, I'll talk about it in a sec. So dose is 2.0. And you can see it just updates. I don't have to go back to ANOVA. It's just updating the ANOVA. And yes, it is non-significant. Well, how did I know that? Well, because they're right on top of each other. The means are right on top of each other. So I would have been shocked if it's significant. There's no way that it could have been. But the point I'm trying to make here is that I kind of had an idea about what I was going to get before I ran it by just looking at the plot. That I think we've talked about in class, but that is a very good habit and skill because you, as you're analyzing data, you will make an error at some point and you will get results um, that are incorrect. And sometimes you'll get results that are nonsense, that they can't possibly be right, or or maybe they could possibly be right, but you'd be very, very surprised if they were right. Well, that's a good signal to go and dig deeper and go, did I code something wrong, or did I put the wrong variable in, or did I store a variable as the wrong name, or any number of little tiny mistakes we could have made. Having that number sense, that idea of like, I know what I was expecting, and this either meets or violates my expectations is really helpful in that regard. So when you see two means stacked on top of each other, you should go and run that test, and it should be, you know, not very much not significant. And you go, yep, that makes sense to me. Okay, well, that's it for this one. Hopefully that's clear, and we will wrap up with just one more lab to go.